edition of the Relatorium Seminar. We're very happy to host Theo McKenzie, who will talk to us today about quantum chaos and real-world networks, which is strikes me as a very interesting combination of ideas. I want to see where Theo will take us. So take it away.
Sure. No, thanks so much for the invitation. It's really nice to be here. I'm very excited to talk to you guys. I just wanted to, why don't I just start by saying that happy Halloween, and the goal of my talk is that this is not the scariest thing that you see today. So the the easiest
Well
the
done.
easiest way for that to happen would be for if there's as much participation as possible. Like I understand that that's the goal of this seminar. So if I prepared a lot of slides, I definitely don't need to go through all of them. There we go. Thanks, Niels. Uh, so um, so yeah, just if you have any questions about anything or you want to discuss anything, slow something down, that's totally fine. Um, all right. For what it's worth, I thought about putting like an old picture of me from Halloween on here, but I was like, I don't want that to be on YouTube. So, all right. For a general outline, we'll just talk about a general introduction to spectral graph theory. So that's the type of math that I'm interested in. I then want to talk specifically about some results in this area, some recent work that's been going on. Like I mentioned in the title, there's an analogy of what we're doing to quantum physics. So I definitely want to touch on that as well. And then we can talk about some future directions, like where this field is going. So just starting with the introduction. I want to just start by thinking about a couple of different problems. So the first problem is you're given some large network. So this could be like a community, this could be a biological network, a knowledge graph, and you want to ascertain like whether you can split it into some natural communities, like whether the graph naturally splits into different clusters. And so, for example, I have two large networks here, and they both kind of look like a mess. But the point is that the first network, it's actually just completely random in terms of I have a bunch of nodes and I've just connected edges at random. But in the second one, I've actually planted two communities. And the question is, how can I distinguish these two situations? And an answer is that we're going to look at what's known as the adjacency matrix. So the adjacency matrix is a matrix that corresponds to the graph. So we have vertices correspond to the rows and the columns of the matrix. And for entries, I put a 1 if there is an edge between the vertices and a 0 if there's not. So for this example here, I have a cycle on 4 vertices. You can see the vertices are labeled 1, 2, 3, and 4. And what you can see is for the matrix, I have a 1 if the two vertices are connected and a 0 if not. So for example, 1 and 2, there's a 1 because the vertices 1 and 2 are connected. So the goal of spectral graph theory is to recover information about the graph just from information about the matrix. Uh, and for an example of how this might work, I I could take two subsets of vertices, so I'll call those S and T, and then I'll define one sub S that's like the indicator on the set S. So it's a vector where I have 1 if the vertex is in the set S and 0 if not. Now, if I look at those vectors, 1 sub S transpose A times 1 sub T just counts the number of edges that go between S and T. So just as an example, if I have S equal to the set 1 comma 2, T is equal to the set 3 comma 4, then 1 sub S transpose A sorry, this should be 1 sub T. It counts the number of ones which is in this submatrix. So there are two ones in the submatrix, and that really corresponds to the two edges that exist between the set 1, 2 and the set 3, 4. Uh,
Can I ask a quick question, Theo?
yeah.
I don't mean to derail this, but a thought that comes to my mind, and maybe it's because I teach this stuff as well, is whether at this point one needs to wonder whether the two fields are essentially equivalent, namely the things that you can say about graphs and the things that you can say about their matrices, their matrix representation. How faithful is it? And I realize you're going to be talking about the spectral side of things, but are there things that matrices cannot tell us about graphs? And is this just something that,
Yeah,
as a background, we want to know?
so that's a good question. And a lot of times in this field, we'll use the two terms interchangeably. Like I'll think about a graph and I'll think about the matrix interchangeably. In terms of the spectral information itself, there are definitely some properties of a graph um, which you can't deduce from the spectrum. Like for example, there's this idea of there's the isometry problem, which is to say, can I tell whether there's an isometry between two graphs? And you could think about the equivalent spectral problem, which is the isospectral problem, which is like if all of the eigenvalues are the same, can I distinguish them? And the point is that there are more graphs which are isospectral than there are isometric. That being said, though, definitely like I remember it was told to me when I was first looking at this that by someone senior in the field that they're very surprised anytime that they see something useful which you can't deduce from the matrix.
Yes, thank you for saying that. And that the isometric problem was the one I had in mind. But what
Yeah,
struck me also as maybe worth articulating is that with the matrix representation, this is for newcomers to the field, perhaps, and it's related to the idea of relatorium, um, is that it's not just the matrix, it's the whole algebraic structure that goes with it. So, in other words, the algebra of matrices is the representation, and
yeah,
so there may be things about the compositionality, let's say, or other aspects of, let's say, the algebra in quotes of graphs that is different from the algebra of matrices. So it isn't just the representation of the object itself, but what can be done to it or what it can do, to others, how they act on one another. That so it when we're thinking about ways in which the matrix algebras might not be equivalent to the graphs, what I have in mind is perhaps these other properties of the graph that don't correspond to the algebraic operations on matrices.
that's right. Yeah.
Okay.
Um, yeah, and you can
Okay.
move like beyond spectral, but yeah.
Yeah,
Um,
exactly.
I will say that being said, like you can look at these, like for example, these are two of my favorite YouTube videos. And just from the titles, you can see like exactly how powerful this idea of spectral graph theory is, right? The first one is miracles of algebraic graph theory. The second one, the unreasonable effectiveness of spectral graph theory. These are, if you're interested in this field, these are both really great, like YouTube videos that give overviews of the field, but the idea is that this is actually quite powerful to look at, to pass to looking at the matrices. Great. Okay. So, and we want to start thinking about intuitively, okay, like what is going on here? So what we're saying is that for this form, 1 sub s transpose a 1 sub t, this counts the number of edges between s and t. Uh, So, uh, if I have a larger value there, that means that I have more edges between the set S and the set T. Uh, Also, something to note is that A is a matrix which is real and symmetric. So what that means is that it has real eigenvalues and eigenvectors. Um, and intuitively speaking, talking in very general terms, what we find is that if I have a larger eigenvalue, like we saw, if I have a larger form here, that means more edges. So in general, if I have a larger eigenvalue in my matrix, that corresponds to clusters that have more edges. Uh, and if I if I want to distinguish the two networks that I showed you on the first slide, then what I can think about is spatially partitioning according to eigenvalues. So let me draw that, let me bring that back. So once again, I want to distinguish between these two examples. One is a completely random network. The other one is one with planted communities. And so what I'll do is that I'll look at the adjacency matrices for these two examples. And if I plot vertices according to their value in the eigenvectors, in the first one, I still get something that looks completely random. But in the second one, you can see that my vertices look like they're being partitioned into two distinct communities. And
Theo,
what if
can,
you,
Theo,
yeah,
may I ask a quick question? Are the
of course.
eigenvectors you're talking about, are they of the adjacency matrix or the Laplacian? I mean, I know this is a bit of a technicality, but does it make a difference?
So right here, I'm looking at the adjacency matrix. If
Okay.
I were to look at the Laplacian, I would see a similar type of partition. Yeah.
Okay.
So yeah, so Ted is referring to I'm in this talk I'll just think about the adjacency matrix, which in some sense is the most simple uh, matrix that you can think about in spectral graph theory. But for many applications, it's actually useful to look at a different matrix. So specifically one that people like looking at is the Laplacian, which in some sense is analogous. If you're familiar, it's analogous to the Laplacian differential operator. But in this case, I'm really just looking at the adjacency operator. Um, any other questions so far? All right. But yeah, so the point is that just by looking at the adjacency matrix, I can distinguish these two regimes. So let's think about another question now, which is a Markov chain Monte Carlo question. So the idea is that you can think about this. I want to sample k numbers from 1 through n uniformly at random, but I'm going to add a condition. And the condition is that no two numbers can have difference less than 10. So for example, 1, 15, 28, 40, that's okay. But 1, 15, 28, 33 is not, right? Because these two last numbers differ by less than 10. So you can ask yourself, how might I do this sampling? Let's say that I just want to sample a set of numbers which satisfies this property uniformly at random. So as a first attempt, something that you might think about is you choose all subsets of 1 through n that satisfy or you look at all subsets of 1 through n that satisfy this constraint, and then sample one uniformly at random. Now, this is of course possible, right? Like I'm looking at a finite set of numbers. But the problem is that uh, this grows very, very large very quickly, right? As it grows as like n choose k, which is something like n to the k, right? And this could become very, very large. So like realistically, if you're doing this on a computer, uh, it would be very tricky for large values of n or k. So actually, what we're going to think about is doing a different algorithm. And the idea is you start with a configuration that satisfies this constraint, and then I'm going to randomly exchange elements of my configuration. Uh, so specifically, I'll take an element inside my set and an element outside my set, and then if they still satisfy the constraint, then I'll swap them. So just for an example, I could start with just the easiest one, right? I could just start with 1, 11, 21, 31. I then sample elements at random. So I could ask, can I replace 21 with 55? So in that case, that's okay. So now my new set is 1, 11, 31, 55. Then I could try to replace 1 with 35. That doesn't work, right? Because I create two numbers which are very close to each other. So I stay with my original configuration. And the idea is that I can iterate this process over and over again. And the nice thing here is that at each step, I only sample from k times n minus k possibilities, right? Because I'm taking something inside my set and something outside of my set. Uh, so this is what's known as the Gibbs sampler, which is an example of a Markov chain Monte Carlo algorithm. And this is something that's ubiquitous in modern data science, as often we want to sample from a very large data set without looking at every single element of the set. Now, what do I want for this? What do I need for this algorithm to work? Well, what I need is ideally is that I only need to do this resampling some small number of times before I get something that's uniformly at random. So specifically, I want this algorithm to approximate the uniform distribution, so the one that I wrote above, very quickly. And if I'm able to do this, then I've created an algorithm which uses a lot less information about the original distribution.
Yeah,
Yeah,
can I say one thing here? It seems to me that what you're doing is you're replacing the original exponential complexity with a sequence of steps, each of which is, you know, small, like quadratic or whatever. And then the question becomes, how many steps? How many of those steps do you need? Because you could, in principle,
that's
still need
exactly
an
right. Yeah.
exponential number of steps. But if it becomes, if you can demonstrate that it's a Markov chain and therefore it converges exponentially, you know, um, then you wouldn't need, you would need a small number of steps to get really close to the limit.
Yes, yeah,
Is that
that's
right?
the point
You were, yeah.
I'm trying to make. Thank you. Yeah. Um, no, this is great. Maybe some of you know, I'm not sure, but Ted was my high school teacher in like 2010. So he perpetually teaches me things, and also especially how to teach nowadays. So this is good. Um, so off of that, let's build some further intuition about this, right? So what you can think about is I'm trying to compare two graphs. The first graph is like the complete graph because which is like this uniform sampling. Because the idea is that you can think about it as I start from any configuration, and then I take one step in the complete graph because that's like sampling uniformly at random. Because every vertex is connected to every other vertex. So if each vertex corresponds to a configuration, the complete graph says that I can get from any configuration to any other configuration. So what we want is to create a graph which is much, much sparser, which is to say that every configuration is now connected to far fewer configurations, but I want that to be a good approximation of the complete graph in a sense. Uh, Now, okay, for the complete graph, if I look at, if I want to be a good approximator of the complete graph, what's the condition that I should think about? And it turns out really what you want is that if I look at any two subsets of vertices, the number of edges that go between that subset of vertices should be proportional to the size of the sets. Right? Because this is to say that the probability that I go from S to T should be proportional to the size of S and the size of T, right? And so a way to say this in a graph sense is that uh, approximately the number of edges that go between those sets is proportional just to their sizes, which once again, I can write S this form, 1 sub S transpose A times 1 sub T. And once again, this is a spectral question. Sounds good?
Um, well, I'm trying to think about it a little bit more, and
Uh-huh.
maybe there's a here as well. So let's pause for a minute because, you know, this is, you know, maybe a good place to take a breather. I'm thinking about you. You said the complete graph. That threw me off a little bit because if the graph is complete, well, you know, it's obviously regular. We know a lot about it, right? So as opposed to, you know, I was thinking you were going to a more general place where we have a dense graph, but not necessarily, we don't know it's complete. And then we want to have a generic algorithm that can sparsify it, if you will, that can sample it in appropriate proportional ways or whatever. So do you see? So I'm trying to figure out where you're getting at here, because if we already know it's complete, you know, it should be fairly straightforward to
Yeah,
do it.
so I guess what I'm saying is this first algorithm, right, where I list all possibilities, all valid possibilities, and then I sample one uniformly at random, right? So that's my first algorithm. In some sense, you can think about that like a walk in the complete graph. So the idea is that I start from any configuration, and then I just take one step in the complete graph. And that step is already uniformly at random, right? So what I want to do is I want to approximate that with a sparsification, which is to say that I now, from any configuration, I have fewer other configurations that I'm connected to, specifically like something like k times n minus k, but I want to take more steps, right? But intuitively, what we're doing is that we want to approximate the random walk on the complete graph with the random walk on this much sparser graph. Does that make sense? Or
So I think it's a matter, and I think I'm understanding it this way, and I'm only
Uh-huh.
saying this now to see if others pick this up, or if this is a question that's on people's minds. So the algorithm you're trying to describe is, in the case, let's say that the graph itself is complete, and we know that it's complete. We want the randomization to be such that you're not oversampling some in one place. I mean, we do know in
Yeah.
principle how we would want the sparse approximation to a complete graph to look. It's analogous to the problem of creating a nicely spread out, like a low discrepancy sampling in some Euclidean product space or something like that when we're doing quasi Monte Carlo or something like that. In other words, we want the sampled points to be far enough away from one another. You're not oversampling nearby things,
Hmm.
something like
Yes,
that.
exactly, right.
Is that
And
good? Yeah.
I guess, yeah, just like vaguely like the property that we want is that for every two subsets of vertices, the number of edges between them is just proportional to the size of the sets. Yeah.
Okay.
So,
Good.
okay. Um, good. Any other questions now? Let me see. Okay. So in general, I just want to say that this type of spectral problem, it shows up a lot. For example, in statistical problems, uh, here's just a list of problems where it could appear. One is this idea of manifold learning, where I obtain a number of points in high dimensional space, and I want to see if it lies on some lower dimensional shape. I can write that as a spectral problem. Finding the complexity of very complex functions has to do with the spectrum of the Hessian. Compressed sensing. So this is this idea. So this is a picture that I took in Bodega Bay. If you look at the picture, you can probably guess it's in Northern California. But the idea is that I can compress my image while maintaining all of the visual aspects from. And then another algorithmic question called Laplacian solvers. But the point is that this type of question, it's somewhat ubiquitous in the sense that, and the idea is always, if you give me a matrix which is derived from the system, can we recover the statistics of the system just from the eigenvalues and eigenvectors of the matrix? So in many of these situations, the type of network that we want to build is has this property that we saw before, which is like being sparse, but still being well connected. And so some examples that we saw, like this is what we want from Markov J Monte Carlo, but also for other examples as well. And once again, we want to think about what does a good sparsifier look like? Uh, so it's easy to say what a bad sparsifier looks like, right? So the idea is that a bad sparsifier is when I can't get from one part of my graph to another part of my graph. So an easy example of this is just if my graph is disconnected. So this is just an example of a bad sparsifier, the complete graph. And then once again, a good sparsifier would have the opposite property, where if I look at any two subsets of vertices, the number of edges that go between those subsets is proportional to the size of those sets. Okay, so
Theo,
yeah,
presumably it's not only the bad thing that can happen is not only disconnection. I mean, obviously that's an extreme one, right? But that you can
yeah.
find from the first eigenvector essentially. You could, but there could be other spectral properties like have to do with higher eigenvalues that presume. I mean, is this am I thinking about it the right way, that like the obstructions or the the bad things you're trying to avoid are in some sort of hierarchy where some are easier to check and then you're progressively checking harder ones, more
To be
sophisticated
honest,
ones?
like really, this second property of a good sparsifier, you basically want to satisfy this as much as you can, right? So this is the first one is like the worst case for satisfying this property. But if you basically satisfy this as well as you can think about it as like a scale from like not satisfying this at all, basically where this quadratic form is like zero, like you're saying, uh, versus for every subset is approximately the same. So really, like when we think about problems here, it's like on a scale of how well do we satisfy the second property. Yeah.
See, yeah. So you can be very, I mean, being zero is a very extreme thing, but you can be very
Yeah.
low and not zero, and that's still pretty bad. So then
Yeah,
spreading it
like you
to the
could
higher
like
place.
if you had instead of d you had 0.001, that would be bad.
Yeah.
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 Oh, all right. So once again, I just want to emphasize that this is a spectral problem. And the idea here is that this contribution of like d times s times t, this really corresponds to the largest eigenvector. So the idea here is that if I have a regular graph, so regular just means that every vertex neighbors the same number of vertices as every other vertex. So on the left, I have a two regular graph. Every vertex neighbors two vertices. On the right, I have a three regular graph. Every vertex neighbors three vertices. But what I can see that is that if I look at the adjacency matrix and then I multiply it by the all ones vector, then every one gets multiplied by the degree. Like you can see, for example, on the left, because I have two ones in each row, then when I multiply the all ones vector, I'm going to get two times the all ones vector. Um, so once again, like big picture, what this means is that the this eigenvector, which is this all ones vector, we call it like the trivial eigenvector, and this exactly corresponds to this contribution that we want d times s times t. So really what our goal should be is that outside of this eigenvalue, all other eigenvalues should be as small as possible, because that will give us an approximation as close as possible to d times s times t.
Yeah,
Yeah.
but Theo, this seems to rely heavily on the regularity of the graph. And again, this relates to my earlier point where I said, for complete graphs. So okay, so the regularity of the sample that you want to, it seems like,
Yeah.
I mean, is this part of the design? In other words, you put it in by design in order for analytic tractability, or
Well,
is it part of
the
the
point
problem?
So the point is that if you have an irregular graph, you can do a similar setup. But the problem is that the matrix becomes more complicated, right? Like it's totally feasible, but you have to use either what people call the random walk matrix, where the entries are not just zero ones, they're more complicated, or you use what people call the weighted Laplacian, which is a version of what you're talking about. Really, the nice thing about regular graphs is that those matrices that I just mentioned, they're all just like simple transforms of the adjacency matrix. So it's really just equivalent to the adjacency matrix. But the thing is that there's always a trivial eigenvalue, and we always want this type of approximation, let's say. Uh, Good. So let's just say that
Are you?
yeah,
I
go
do
for
have
it.
a question. I presume your whole talk is about finite graphs. Do you
Yes.
with infinite graphs?
So there is stuff that we can say about infinite graphs. So you can associate uh, an adjacency instead of a matrix, right? You look at an adjacency linear operator with infinite graphs. But the nice thing is that once again, that has some associated spectrum, and the techniques that we use can actually deduce stuff about that spectrum. So there is stuff we can say.
Thank you.
Yeah. Uh, so so for the adjacency matrix for a graph, uh, I know that once again it's a real symmetric matrix. So I my largest eigenvalue is always D that we saw here, and I have other eigenvalues. And really, what I want is to say that all my other eigenvalues are as small as possible. And oftentimes, what people will say is that this is called the spectral expansion. Uh, and this is a measure of how well connected our graph is. And really, our goal is to have this spectral expansion, so the maximum modulus of all the other eigenvalues to be as small as possible. And our goal is going to be to find regular graphs. Once again, this is just for simplification with lambda as small as possible. All right. So let me explain what we've done. Any other questions right now?
I'm wondering if lambda as you had, if you pull it back the previous slide, if it relates also to what we talked about earlier. In other words, if it plays kind of the role of the spectral gap, like in the sense of the speed of convergence, the number of steps, how
Yeah.
so is that a related concept here?
Sure. Yeah. I mean, yeah, it's very much related. Uh, People often, you can basically bound the rate of, people talk about the mixing time of the random walk. So if I have a graph and then I step from one vertex to a neighbor, etc. This is also encoded in the adjacency operator. So you can bound that mixing time in terms of this parameter lambda. And once again, the smaller that lambda is, the quicker this mixing time is. Yeah. Uh, Good. Any other questions? Okay, so let me talk about just the statement of results here. So the idea here is that, yeah,
Question
go for it.
muted when it came to me. Related to Ted's earlier question about adjacency matrices relating being as informative about graphs as the graph data structure itself. It seems to me that the answer should be yes in a natural sense, category theoretically, and that's one of the things that we in this group are kind of interested in is category theory. And that is you can define a notion of a morphism of adjacency graphs in such a way that you get a category that will be categorically equivalent to the category of graphs with edge preserving morphisms, for example, edge preserving maps. And so you can study isomorphism and all the natural properties of a combinatorial object in that sense. And then you get that any first order property of graphs can be transformed into first order properties of adjacency matrices in that category. That's my expectation. I don't see why it wouldn't be the case. I think, so especially for finite graphs, and probably for infinite graphs as well, if you're talking about the operators on the linear operators being on characteristic 2 vector spaces, Z2 spaces.
Yeah.
Yeah.
Yeah. So, for example, so that's really interesting. Definitely, yeah, something that I'm interested in, even though I haven't thought about it too much. But I think one thing, thinking specifically about infinite graphs, is a lot of time what we struggle with is like, how do we come up with a nice definition of an infinite graph? So a lot of times what people will think about is this idea of like people call it unimodularity, which is this idea that an infinite graph is like a distribution on vertices, but it's a distribution on like an infinite set of vertices, and basically, the each vertex has a neighborhood that you can look at, and so that's a basically this is an interesting question in itself, right? It's just like thinking about a nice idea of infinite graphs. So.
Thank you. Like Ted, I don't want to derail it. I just wanted to put it out there.
I mean, I think once again, at least from what I understand, this is the point of the seminar. So this is good. There's nothing worse than a Zoom talk where everyone has their screens off and you don't know whether everyone is asleep or not. So this is good. That you don't need to now turn on your screen just because I said that. It's okay. Thanks. Um, so Anyway, I'll talk a little about definitely I won't get through everything that I wrote, but that's fine. Uh, so I'll talk a little bit about like what is an optimally expanding graph. Um, and very briefly speaking, uh, there's a natural limit of how good my expansion can be. If I want these to be as small as possible, then there's something that's known as the Alma-Pana bound, which says that lambda 2 is always at least this specific number 2 squared du minus 1. And actually, to Matt's point, this actually has to do with this correspondence between finite graphs and infinite graphs, which I won't get into now. But the point is that I'll always have a value at least 2 squared d minus 1. And so if I want to be as well expanding as possible, then I'll have all of my eigenvalues satisfy this bound of 2 squared d minus 1. And so Lubotsky, Phillips, and Sarnak gave this definition where a graph is Ramanujan if every eigenvalue which is smaller than d is smaller than this bound 2 squared d minus 1. And so this is named after Srinivasa Ramanujan because the way that they were first constructed is by using what's known as the Ramanujan conjecture. So basically, I can think about Ramanujan graphs of two types, which is a graph can be bipartite or non-bipartite. Bipartite means that I can divide it into two sets such that every edge goes across the set. And non-bipartite does not satisfy that. So constructing these Ramanujan graphs has been a long-standing and celebrated problem. So originally, these were created in these works by Lubotsky, Phillips, and Sarnak and Margulis. And they showed Ramanujan graphs when D is equal to P plus 1, where P is a prime. Then Morgenstern generalized this when D is equal to P to the K plus 1, where K is some integer power. And then Marcus Bielman and Sarastov completely solved the existence problem for the bipartite case, where they showed that for every degree and every number of vertices, there exists a Ramanujan graph. However, existence of non-bipartite Ramanujan graphs, so these optimal expanders, had remained open. And this is also interesting because it would give you more examples of bipartite versions. Now, I wanted to talk just a little bit about how you construct these. And I'll just give simple examples. But the idea is, how do you construct graphs which are good expanders? So one simple idea, is that you can use arithmetic. So to create a graph on n squared vertices, I could have each vertex correspond to an ordered pair, ij, for 0 is less than or equal to I minus 1, less than or equal to n minus, 0 is less than or equal to ij, less than or equal to n minus 1. And then vertices correspond to these ordered pairs. And then I'm going to create a rule which will define the edges. And this is connect ij to I plus minus 1j and ij plus minus 1. And this will give me what's known as the torus graph, right? Because what you can see is that I basically have two cycles, one corresponding to the first dimension, one corresponding to the second dimension, and then I'm basically gluing these together. Okay, so it turns out that go for it.
Sorry. I think just because this is interesting and you said it a little bit quickly, and in the interest of making sure we're holding people together with this, I don't want to brush it aside. I think this is a really cool idea. For example, the idea that it is pairs of numbers that correspond to nodes, like the first thing I might think, a non-expert might think, a student, for example, might think, oh, the pairs are really the edges, but here you're saying, and I'm buying time for people to think about this a little bit as well, right? That the nodes are the pairs, and you connect nodes with edges that go to nearby numbers in the pair, whether in the first component of the pair or the second component of the pair. And that's why you get the two cycles, one that connects along the first component and one that connects along the second component. Am I thinking about it in a
That's right, yeah. And really, you could choose any length, right? It doesn't need to be ordered pairs. It could be like ordered k tuples, and then you would create like a k-dimensional version of this. Yeah.
Right.
So
exactly.
This can be an example of a way to build a very regular nerve of a covering of certain coverings of a torus in topology as well. So that's, at least I think it looks like that's kind of what you can, one thing you can do with this, but the covering has to have a regularity property as well. So yeah, okay.
No, these are all good points. So I'll just say, okay, this gives a torus graph. Yeah, but the point, yeah, like Ted is saying, is that I'm just, you can think about this geometrically where I'm just connecting vertices to nearby points. But an idea of how to build an expander is I could just create a somewhat more complicated rule. So maybe the simplest rule is I'm going to take the torus, but then I'm also going to connect ij to I plus or minus j, and also I to I, j plus or minus I. So this is one of the first constructions of a expander. So ones where my eigenvalues are very small, that exists. And I won't prove this, but this is actually an expander. And in fact, the way that Lubotsky, Phillips, Sarnak, Margulis, and Morgenstern construct their Ramanujan graphs is the same type of idea, but instead doing it for groups. So here, vertices correspond to elements of my group, and then they're connected if GH inverse is a generator from a prescribed list. So if it's been a while since you've done abstract algebra, that's fine, but the general idea is that we just want to create like slightly more in-depth rules and then connect vertices based on those rules. Okay, yeah, go.
Sorry, is there modularity to the required operation?
In what sense?
In other words, is a cycling or you know, I don't know if
everything is mod n.
It will guarantee that it goes. You know, I'm just wondering, is there some sort of modularity condition on the type of on this construction for the construction to work to be an expander, or would any choice of set of generators work?
Oh no, you need to. So okay, an interesting question that a lot of people are interested in now is whether if I take a random set of generators, whether that works. But for most of these constructions, what you'll do is you'll take a prescribed list of generators. Yeah, like these original constructions, they say it's a specific rule. You say, if I take these generators, then I get a good expander. All right, so let me say, okay, what's the other way that people previously have built expanders? And that's with this idea of the probabilistic method. So this was made famous by Paul Erdos in this famous book. And the idea is that if I have a distribution of graphs, and I know that the expectation of a statistic is below a certain threshold, then there also exists an element of that family for which the statistic is below the threshold. Which is to say, like, if I take an average, is all that this is saying, but it's quite elegant. If I take an average of numbers, there exists one of those numbers has to be at most that average. So a simple example of this is that if I have a graph, every graph has a cut into two parts that cuts at least half of the edges. And the idea is that if I take a random cut, that cuts exactly half, an expectation that cuts exactly half of the edges. So at least one cut cuts at least half of the edges. Now, using a lot of very new techniques, but the idea of this other construction of Ramanujan graphs use this idea of the probabilistic method. So really the statistic that they're looking at, which is quite surprising, is the characteristic polynomial of the matrix. So this is something that encodes all of the eigenvalues at once. And the very surprising thing is that, in fact, what you can do is that you can literally just average all of these polynomials. So the average polynomial just takes the average of each coefficient. And what they show is that this average polynomial has a root which is bounded by 2 squared d minus 1. So there must exist some original graph which has root at most 2 square root t minus 1. So this is definitely not something that always works. You can't just take two general polynomials to average their coefficients and then reason about their the relationship of their roots. But in this specific case, they show that this is possible, which is very surprising.
When you say this specific case, you mean the case where these are characteristic polynomials for
Of graphs. Yeah.
graphs? Yes.
Yeah.
Connected, not regular necessarily.
Actually, yeah, regular graphs. Yeah.
Regular. Okay.
So basically, I fix my degree, I fix my number of vertices, and then I just take the expected characteristic polynomial over all graphs that satisfy that. And I just wanted to say just as a personal tidbit is that this was really what got me interested in this area is this result. Because this happened around 2013. And I was blown away by like how elegant this proof was. And actually, when I went to Berkeley, my advisor was Nikhil Srivastava, who's one of the authors on this paper, and really got me in this area.
So immediately a more general idea comes to mind. What do you get if you consider not what people usually call randomly in terms of uniform distribution, but other distributions to do the sampling for the
so basically they create a set of rules where, like, for example, if I take a weighted average of my polynomials, it will still work, right? But basically, I need to satisfy certain requirements, which they call basically any two things that you average need to be a small perturbation, a rank 2 perturbation of each other. Yeah.
Okay. Thanks.
No problem. Okay, so what about random graphs? Are random graphs Ramanujan? So there are many ways to generate a random graph. I'll just, in interest of time, I'll just go a little bit quicker. But you can take any of these ideas, which are like, I'm going to sample a graph uniformly at random. I just take a set of random permutations, random matchings, or I could basically take all of my half edges and then randomly extend them. So all of these ideas are basically equivalent, but the idea is that all of them generate a random regular graph. So no-go alone conjecture that with high probability, a random graph will be almost Ramanujan. So this was known as Alone's conjecture for a long time, and then there was a celebrated proof by Friedman who showed that indeed it's almost Ramanujan, up to some small error. There have been other proofs since then. But in terms of showing it's actually Ramanujan, this behavior led to a now famous wager between two Princeton professors. So no-go alone wagered that a random regular graph is Ramanujan with high probability. So he thought that this is something that is quite ubiquitous. Whereas Peter Sarnak thought that being Ramanujan was a specific property that was solved by something that solved these specific algebraic equations. So we had this really interesting situation where it wasn't exactly clear what the correct behavior should be. So let's see. Let me actually skip this. Actually, no. Let me say this, which is that this led to a conjecture that if I look at the distribution of the second largest eigenvalue, then it should converge to the distribution of a large Gaussian matrix, of the eigenvalue of a large Gaussian matrix. So the idea here is just that I take a matrix with where entries are Gaussians, and then I sample one at random and I look at the distribution. And actually, based on computer tests, it seemed that the second largest eigenvalue of a random regular graph converged to the same distribution. So if this was the case, then this would mean that approximately 69% of regular graphs are Ramanujan. So technically speaking, neither of these two sides of this wager would be correct. It's actually something in the middle where a little bit more than half of all graphs are Ramanujan. So let me skip this, but let me just say that what the a result that we showed last year is that, in fact, this conjecture is true. And we're actually able to show that if I look at the distribution of this eigenvalue, it's the distribution of this random matrix. And consequence of that is that a little bit more than half of all d-regular graphs are Ramanosian. Okay, does the at least this part of the result, does it make sense?
So can we try to say this in, more vague but maybe more direct sense in words? So for example, I mean, like that's, you were trying to just do that, but can you, in other words, bring together all these strands but without the technical, specificity? The a large number of d-regular graphs, more than half, but not all, are non-partite Ramanujan or something, which means that they have very small, sort of, in some sense, spectral gap, or
Yes.
yeah.
Yeah.
No, very large spectral gap.
Very large spectral gap, yeah.
Very large spectral gap.
Uh-huh.
Okay.
So yeah, that's exactly what we showed. Like it wasn't clear whether most graphs had this property or almost none, but it turns out that a little bit more than half have this property.
And the intuition behind it is that there's some sort of central limit theorem type of, or some normal distribution playing a role there, for some reason.
Yeah, this is basically like a high-dimensional central limit theorem. The intuition really comes from quantum chaos. I realize I'm almost out of time. Maybe I'll talk about that just for
Yeah,
a couple minutes.
we can go, 5 or 10 minutes past the hour. It's okay.
Yeah, I'll try to be punctual, but I at least want to say an intuition. I'll at least try to give an intuition for like why this might be the case. How about that? Okay, so let's see. So let me talk, yeah, just like for a few minutes, just about this analogy to quantum physics. Um, so quantum physics originated from this problem of Einstein, specifically looking at the photoelectric effect, where he observed that he created a model where light consists of tiny packets of energy, so like quantized bits of energy. And using this model, Einstein was interested in studying the spectrum of larger atoms. So Bohr successfully used quantization to study the spectrum of a hydrogen atom. So Einstein was interested in studying models with more degrees of freedom. So let me actually uh, so let me actually skip this part. Or no, let me say this, which is that uh, Einstein was able to do this, but he had to make a bunch of assumptions about the model. So he was able to study the spectrum, but assuming that there were a lot of patterns associated with the model. And basically, this creates this dichotomy between integrable systems and chaotic systems. So the idea of an integrable system is that it has many patterns. So this is like a billiard ball bouncing in a square domain, where if I slightly change the trajectory, I'm not going to, or I slightly change the direction, I'm not going to change the trajectory that much. And the other type of system is like a chaotic system, which is like a billiard table, but now I put a circular bumper in the middle. And the idea there is that if I slightly change the direction, then I greatly change the trajectory because there's no patterns of the system. So something that Einstein noted in this old paper, in this 1917 paper, is that in the real world, we typically have ergodic systems, so systems that look like the right-hand side. But even though his solution is for systems that look like the left-hand side, for integrable systems. So, okay, so as quantum mechanics developed,
can I ask?
yeah,
Can I ask a question here? I don't mean to derail it, although this is so. In other words, feel free to keep it for later. For after,
yeah,
if there's time. I'm intrigued by your use of pattern, of the question of pattern, and whether there is no pattern, possibly one pattern only, or multiple different patterns. And so what I have in mind is that there's on the right hand side, you say there's no pattern in trajectory space, in path space, but on the other hand, there's a unique limiting distribution, right? Namely, it will fill out. There's no matter where you start or what angle you're going to use, essentially, except for measure zero, it's going to be filled in, in the same way. It will look the same in the end. Whereas in the left-hand side, you get stuck in a particular pattern, and there are different patterns. Now you can say they're equivalent, and there might be even systems that are somewhere in between where there are inequivalent multiple patterns. So I think that's missed a little bit by that distinction. In other words, there's ergodicity, and then there's integrability, but there's also non-ergodicity that might not be integrability either.
Oh, sure. Yeah. This is like a very stark simplification of,
Well,
yeah.
this is a very classical distinction,
Yeah.
which I think nowadays
Yeah.
we're, so, okay. Yeah.
Sure. Yeah. Okay. So the point is that, based on the work of Schrodinger and Born, we now often think once again about the movement of these electrons, not only in terms of these classical dynamics, but also in terms of these what we call like quantum dynamics, where there's the Schrodinger equation, and which is a differential equation, which once again has an associated it has associated eigenfunctions and eigenvalues. And if I want to understand the wave equation associated with an electron, then I can look at this Schrodinger equation, and something I can do is try to decompose it into these eigenfunctions and eigenvalues. So Einstein's question in the spectral sense, in the wave equation sense, is what does the spectrum look like, and what's also the distribution of these eigenfunctions for an ergodic system? So I think this is the slide that I really wanted to get to. Uh, and the idea is that uh, Eugene Wigner wanted to study the spectrum of very large nuclei. Uh, so what he noticed is that even though it was basically impossible to solve the Schrodinger equation directly, what he noticed is that it didn't matter the specific parameters of the nucleus, but what seemed to be uniform is the gap between eigenvalues for the nucleus. So this is looking at the spectral lines associated with hydrogen, so the different colors of light emanated by hydrogen versus uranium. And what he noticed is that if I look at the gap between these spectral lines, they basically they seem to follow always the same pattern. And the surprising thing, yeah.
Just to be clear here, you're talking about the ionization levels of the different ionization levels of the atoms, depending on the size of the nuclei. And that even though obviously a richer, atom has a much finer, set of ionization energies, because there's a lot more electrons. But in reality, the pattern, the scaling pattern of the gaps is the same, is a universal law, essentially. Right.
Yeah, so basically, if I take any large nucleus, and then I just look at the gap, the distance between spectral lines, then that gives a distribution, right? Just of different lengths. And what Wigner realized is that that distribution seems to be uniform. It seems to not matter on the actual atom. Yeah. And I guess the surprising thing there is that he showed that it's the same as the gaps with a GOE matrix.
Right. So it scales. I think the point that you're making here is important. It scales not exponentially as one would. I think at the time they were expecting that it might, because, eventually you get the complete, dissociation of the electrons, you get the continuum part of it. And they thought that the approach to that was exponential, but in fact it's doubly exponential, it's like doubly exponential. It's a different, and that was surprising. It was an empirical, I mean, at the time when they realized it empirically that it was the case, was surprising. And I think he came up with a theoretical, well, at least, I don't know if at the time it was more of a phenomenological thing, or there was the justification for it was there, the theoretical
There wasn't a
justification.
justification. So you can see like it's called, they called it a surmise, right? So it's the Wigner
Yeah.
surmise. And it's this idea that you're saying that like basically eigenvalues want to repel each other. And you're right, if they were if they were independent, like if the eigenvalues were all independent, it would be like exponential. Um, and the general idea is that, and this is something that Wigner noted, is that if I look at a random matrix, then I get the same type of repulsion. So both of these are from Wigner's original papers, right? And for example, on the right, he samples 197 20 by 20 matrices, which for the 50s is pretty good. And he shows that the gaps between eigenvalues, or
Did he do
the
that by
distribution.
hand? No,
No,
like one of
I'm
those,
sure he used a primitive computer.
like an
Yeah.
ENIAC or
And
something.
I'm sure it took like 2 weeks to do this or something, uh, but yeah. Um, and like no one else could do any calculations for those 2 weeks or something like that. Um, but yeah. But anyway, let me just say, I'll skip this. The general, in general, what we do is that uh, there's a general conjecture, let's say, that if the classical dynamics that I showed you at first, so like these billiard ball dynamics, if those are chaotic, then the spectral properties should also be chaotic, in the sense that they should have statistics like a Gaussian matrix. Uh, However, I can come up with specific examples where that's not the case. But once again, these come from number theory. So these might be super specific to those examples. So what we could ask is, if I have a generic system, does it satisfy this conjecture, where the classical dynamics being chaotic imply the quantum dynamics are chaotic? And that's basically what we're studying on the graph. And that's the way that we think about the problem on the graph. So using a discrete graph has been used as a model for quantum chaos for a long time, at least since the work of Kodos and Solansky in the 90s. And really what our result is showing that this conjecture is true, in the sense that if I look at a random graph, then it has these Gaussian matrix dynamics. And I'll just say in words that really the way that we analyze it is through thinking about it like a quantum chaotic system, and using some parameters there. So I think I'll, in interest of time, I'll just stop there, but I'm happy to talk say anything about just like in terms of like methods, in terms of like what we're looking at next, or any other questions that you have just about this analogy.
Okay, well, let's thank Theo first of all for his time. Let's see, we're going to do the reaction thing. Yeah, thank you. Thank you very much. I think you managed it. You managed to stay very close to time, and despite all the interruptions, that and I'm sorry to take so many liberties with my former student here. This is
No, I mean,
in the interest of conversation.
This is way better than the alternative, trust me. Like
Yeah.
I've done the alternative, and that feels way worse. So yeah.
Tell us, I mean, since you have this up here, and I mean, I'm intrigued by the scaling, and this, I know that in these, previously I said central limit theorem, but in a way, this is different. This is a non-classical convergence because of the power 2/3. Like, where does that come from? That's not a canonical power.
Yeah, I mean, you could think about like, even for the central limit theorem, like you have to renormalize by n to the 1/2, right?
That's
And
right. It's 1/2 is the normal, the normal scaling.
yeah. And the idea there, right, is that like that's like the typical fluctuation,
Yeah.
right, of the sum. So we have a similar idea here, which is that if I look at the difference between, let's say, lambda 2 and lambda 3, if you just look at the semicircle law, because people call it the square root edge, where like basically if I take a semicircle and I divide it, basically I divide eigenvalues based on that semicircle law evenly, then the difference between the last two eigenvalues is like n to the minus 2/3. So that's basically the amount that we have to normalize by. But that's also true for the Gaussian matrix. That basically, if I look at the typical distance between two edge eigenvalues, it's like n to the minus 2/3.
Interesting, interesting. So it's like an arcsine type of argument analytically.
Yeah, I mean, the idea is really, yeah, if I look at if I look at Wigner's original model, so people call it Wigner's semicircle law, then yeah, basically because it looks like just like a semicircle, you could think about it like an arcsine type deal, but really just like the last two eigenvalues typically differ by n to the minus 2/3. Yeah. Whereas in the middle of the spectrum, eigenvalues are much more packed together.
Right, right, right. So
yeah, and it's like
just I was just thinking analytically, like, as an approximation, like and what are we to expect in other, in other instances? I mean, was this something to be expected then? Therefore, it wasn't like phenomenological anymore. It was like conjecture
I think at this point, I would be surprised if at a large scale, like statistics of random regular graphs don't agree with Gaussian matrices, right? So the Gaussian matrix, it's nice because once again, it's like completely solvable. So we have an explicit form for like density of eigenvalues. So that's been known for a long time, like since the time of Wigner. So I would have been very surprised if we didn't have that n to the minus 2/3 or really like any other difference.
Okay. Well, are there any other questions or thoughts, ideas before we stop the live stream?
I wanted to just maybe a very general question, because I'm personally very fascinated by complexity theory and like Kolmogorov complexity. And I see a lot of connections, right? Because the chaos is the difficulty to describe it with little information. But is there like, you've talked about eigenvalues, which is a particular measurement, but I guess there's other measurements as well, right? I just kind of curiosity if it's how much it is explored from this angle.
Yeah, do you have anything in particular in mind?
Well, I'm more thinking about like, is there like a language for building graphs, right?
Yeah.
And then seeing what are the simplest graphs to make and what's actually difficult, a chaotic graph to make, right?
Sure.
Beyond.
And just to add to that, and I don't know if this is where you're going to, Niels. I think this is close to what I had in mind now that you were saying it early on when I started. And I guess, Matt related a little bit to that too, but on the other side. So I beg to differ in this case with Matt, and which is that maybe the spectral, the things that are encoded by the spectral distributions and so on, and in some ways linear properties of the graph. But the graphs in some sense as a language might have other components that are not linear. I say linear, I mean in a compositionality aspect, which an algebraic structure on top of the matrices, and that's captured fully from the eigenvalues. And we're delving deeper into that sort of linear statistic. Perhaps that is why we get normal distributions. But there may be, if we see graphs as a means, as a language for encoding information, there may be more ways that they can be used to encode information than like as combinatorial objects that are not necessarily playing well with the linear algebra of their matrix representations. Making sense.
No, and I think these are interesting points. I think one thing that I want to highlight, which is one of the slide that I skipped actually, is that we're actually very bad at thinking about how to construct graphs, right? We basically have a very small number of ways that we can think about constructing these, like either like embedding them into Euclidean space because we know how to do that, using number theory, like using this probabilistic method or random ones. But like, sometimes, like Avi Vingerson in Princeton, like he has this phrase that he likes to use, which is like finding hay in the haystack, right? Which is that we're all the examples that we can think of are like very specific. And like I guess one of the advantages of these random graphs is that like if you can think about a property which is more generic, then you can if you can reason about the random graph, then you can get something that's uh, that maybe isn't satisfied by any of these specific examples. But that being said, we use very technical, like our paper, right? It's like 150 pages, right? And it also uses like previous results as well, and uh, it's very hard to do that. So I think maybe at least one way that I can interpret the questions that you guys are having is that like we're very bad at constructing graphs, and it would be nice if we had like easier ways of like thinking about different types of graphs which have any property that you want, like linear or nonlinear. Yeah.
Thank you. Yes, there's much to think about. I think I mean, compared to, I think I told you this before, Theo, that back in the day, I don't know, 30 plus years ago, 35 years ago, when I was studying my graduate school work, and this sort of the spectral theory of graphs, random graphs, was very much in it, new and exciting, and especially in the context of Monte Carlo, Markov chain Monte Carlos and so on were just being
Hmm.
created. You and the cohort of people you described have pushed the envelope very far in terms of the technical things we wanted to see, in terms of really strong statements, very strict statements about the spectral gap. I suppose you give us a lot to think about, especially the connection, I think, with quantum chaos, where the elements that are being quantized are not you know well, in other words, there are distributions, there are other kind of algebraic objects. Let's say the matrices play a dual role. They're not just like the elements of the matrix are not necessarily just points in a graph, but they could be qubits. The whole matrix itself could correspond to different abstract states, for example. And I'm just saying that this, what started off as being what at the time seemed to me to be a fairly concrete language about things that we were interested in, by working at it for all these years now and attaining sharper and sharper results, it has become abstracted to the point where now it can mean lots of different things as well that we wouldn't have imagined, more abstract things that we didn't imagine at the time would be possible. So this is a small example of mathematics in the making, where you kind of come up with the abstractions, and then they take a life of their own, and they could find applications and meaning that wasn't thought of at first.
Yeah.
So
I'll say just quickly off of that is that right now is like a very exciting time in spectral graph theory. Uh, like there are a lot of very interesting new results using very powerful methods. And something that I'll just mention briefly is that there's also been recently a lot of interesting connections also to just like differential geometry on hyperbolic surfaces, which is another area where recently there's been a number of like huge breakthroughs. And a lot of them come from taking these techniques that are used for graphs and then applying them to like the spectral theory of these hyperbolic surfaces. Just something that I wanted to mention.
Yeah, I mean, the connection between graph theory and differential geometry is classical, but the
Yeah.
idea of using these techniques, these ergodic techniques for the study of hyperbolic spaces, obviously was very much pioneered in the 2010s, largely. And Mirzakhani's result, for example, was big, and I'm really glad to see this actually maturing. A connection I had in mind, and maybe even Nathan and certainly Niels know about this, but connections with logic. In other words, graphs arising from different logic models. And, that, for example, in cryptography or in even quantum cryptography and That's another. But I mean, the graphs as data structures. I think somebody said that, maybe it was Niels or Matt. Graphs as data structures are becoming a thing. There's certainly a category of graphs and of various kinds that people in applied category theory are thinking about. And so that's a bit of the tradition from which we approach it. Like, it's a versatile kind of object, and it has with it these series of questions, including the spectral ones that you're addressing here. And it seems like it captures ways of thinking about different other types of objects, whether they be hyperbolic surfaces or codes or just different alternate logics and so on. That I think is very exciting. I'm very glad. And also, okay, as a little bit of an aside, the fact, Theo, that you've come to a point, I don't know, not that long, maybe 12 years or so after you graduated high school, to write a math paper of over 150 pages. I think that would have been unthinkable, at the time. That it's something I'm going to be telling my students who have a hard time thinking about writing anything mathematical that's more than a page or so. So
Yeah. No, that's another reason why I'm excited to speak in this seminar, is that, if someone knows you when you're 16 years old, right, then they know where the bodies are buried. So you better do everything that you can to be nice to them. Uh, I'm just kidding, but yeah.
oh yeah, no, I'm very proud of you. Thank you for joining us. Thank
No,
you for
thanks for
taking
the
the time.
invitation.
Yeah.
This was very nice. So.
And Niels, you can stop the live stream if you haven't already. So we're good. Okay. Yeah, I don't know
And I
if
don't want to jinx it, but no Zoom bombs.
no,